Today, on how it's made. CCD Semiconductors, making your digital photos picture perfect. Airline meals. When they make them, they aren't just winging it. Paper cups. We pay lip service to the manufacturing process. And trumpets. We visit a factory that always manages to blow it. A CCD semiconductor is the image sensor in a digital camera or camcorder. When you snap the shutter, you expose the CCD to patterns of light. It records them electronically by converting them into millions of electrical charges. The camera's processor then reads these charges and translates them into the image you photographed. CCDs, or charge-coupled devices, are made of silicon, the main element in sand. What's special about silicon? When light hits it, you get electrons. Production begins with a round silicon wafer 15 centimeters wide and about as thick as a shirt cardboard. It goes into a steam oven for 3 to 4 hours. The intense heat, along with the oxygen and hydrogen gases in the steam, create a glass-like layer on the wafer. This insulates the silicon against the miniature electrical circuitry they'll build onto it. But before making that circuitry, they cover the wafer in conductive material. This conductive layer measures less than a micron. A human hair is 100 times thicker. Onto that, a robot applies a 1-micron thick layer of photosensitive resin. When exposed to light, the resin will undergo a chemical reaction. A technician suspends a mask over the wafer. The pattern on this mask is the schematic for part of the circuitry. When you take a picture, you expose the silicon wafer to light, and that generates electrons. The circuitry carries those electrons to the camera's processor, which reads the charges and translates them into an image. This machine exposes the masked wafer to ultraviolet light. The resin shielded by the lines of the circuitry pattern remains intact, protecting the conductive layer beneath it. The resin on the areas not masked by the circuitry pattern breaks down and becomes vulnerable to specific chemicals. The next step is to spray the wafer with those chemicals. This dissolves the resin, exposing the conductive layer underneath. Technicians repeat this entire process with anywhere from 13 to 30 masks until they've built up the full circuitry pattern on the wafer. Next, technicians submerge the wafer in acid, which eats away the uncovered conductive layer. So now, the only conductive material left on the wafer is the actual circuitry, the unexposed resin coating having shielded it from the acid. Next step, a thorough rinsing in ordinary tap water to remove the residue. Then a rinse with purified water to remove any impurities left by the tap water. Throughout production, contamination is a concern. Just a single speck of dust can ruin a wafer. To protect and insulate the circuitry, they coat the wafer in liquid glass, then bake it for 2 hours until the glass solidifies. The wafer surface is divided into 25 million tiny square cells called pixels. When you take a photo, each pixel records the light intensity of a minute portion of the scene, generating an electrical charge. A filter on the CCD translates each pixel charge into color. The company makes this filter with 3 pigment powders: red, green, and blue. These 3 colors combined can reproduce any color. The camera's processor reads and then reconstructs the photographed scene pixel by pixel. Each finished CCD undergoes a battery of automated tests to ensure that all the circuits are functional. This machine marks faulty circuits with ink. Just one bad circuit is enough to discard the entire CCD. Technicians then check every CCD under a microscope, looking for scratches that might have occurred during the production process. This CCD with 25 million pixels is called a 25 megapixel CCD. The number of pixels on a CCD varies depending on what type of camera it's for. This company even produces a single CCD that has 111 megapixels. So, the next time you say cheese, remember that you're producing a digital photo thanks to all that painstaking work that went into the sophisticated CCD semiconductor inside your camera. In the earliest days of air travel, passengers really lived the high life. There were multi-course meals that were actually prepared during flight. But as air travel increased, this became impractical and airlines turned to pre-made meals. Because when you're feeding a lot of people in a small space, it's best not to leave dinner up in the air. These are meals meant for a higher purpose, as in feeding folks at an altitude of thousands of meters. That's why you don't see any soufflés here. They couldn't possibly rise to the occasion. It's just one of the things they consider when preparing airline meals. Airline meals start with loads of ingredients. They make 45,000 meals at a central facility in one day. Of course, the cooks wash their hands very thoroughly because they don't want any germs stowed away in the meal. They cook on grills that are 1.5 meters long. At one end, they stir-fry a big batch of veggies, while at the other, they sauté potatoes. They spice it up. Airline food isn't really all that bland, but the atmosphere on the plane may affect our perception of it. It's believed that low humidity and the pressurized environment cause our taste buds to work less efficiently. Something to take into account when you're traveling. The recipes also vary according to the route. Flights to more exotic locales will offer spicier dishes, while a domestic North American flight usually calls for a little less seasoning. They fire up different grills for the meat. They're making meals for the crew as well as the passengers. On many airlines, a pilot must eat a different meal than his counterpart to minimize the risk of food-related illness compromising the flight. The cooked food will now be blast chilled in special fridges. They scrub up again as they prepare to assemble the meals. They start with the food that's to be reheated on the plane. It goes into foil containers. Smaller containers inside help to control the portion sizes. They're careful not to overstuff them because that could cause messy spills later. Some sauce, and a generous dab of butter, and you have the makings of a first-class meal. They put the lids on and make sure to vent them. With each menu change, the chefs meet with airline representatives. They serve up sample dishes and discuss the ingredients with them. There's often a lot of negotiation before a menu is settled on. Every detail is planned, right down to the plates and bowls and how they're to be arranged on the serving tray. It takes a bit of arranging to make everything fit. Once they come up with a spot for everything, they follow that formula in the kitchen. As with any meal, presentation counts for a lot. Of course, meals for passengers in the economy section are more simple and the planning less detailed. The food-laden trays all go onto trolleys, and they roll them into a big refrigerated room where they're arranged according to the flight number. They won't be here for long because every meal made is to be served that day. And all the groundwork beforehand is sure to pay off once passengers and crew are en route. The paper cup was invented around the turn of the 20th century to stop the spread of disease, and the concept continues to hold water. It's a hygienic way to quench your thirst or get your morning cup of Java, and the lining of plastic or wax keeps it watertight, preventing any nasty leaks. Coffee, anyone? With paper cups, you can have it to go. They start with paper that has a thin plastic coating. It unrolls into a printer that's as long as a bowling lane. The paper weaves through the printer in a continuous ribbon as printing cylinders at each station layer an image onto the paper, one color at a time. When the image is complete, a rotary die cuts the paper into a flat. The dimensions of the flat vary depending on the size of cup being made. Each flat will eventually be a paper cup. They land on a conveyor in a shingle-like lineup. A computerized system counts the flats and divvies them up into stacks of 200. The flats drop into an elevator stacker. It piles them one on top of the other so they can be easily collected by workers. They load them into another conveyor in a different part of the factory. It moves the flats in a vibrating shuffle up into the cup machine. Meanwhile, a roll of paper winds into the other side of that machine, where a die punches out bottoms for the paper cups. This leaves a long strip of scrap paper, which gets sucked away for recycling. A device grabs the flats and relays them to a carousel. Now the paper cup takes shape. Mechanical jaws wrap each flat around a mandrel, and a heat gun seals the seam. And now you have a paper cup with no bottom. Its life will surely be empty without one, so that goes on next. Bottoms are shoved onto the cups and heat sealed in place by melting the plastic backing on the unprinted side of the paper. The cups then fall down a chute to the next operation. This one will give the cups a rim, allowing you to take a sip without spilling. A hot tool curls the edge of each cup into a rim. Then a vacuum sucks each cup into ductwork overhead. Each piece of ductwork comes from a different production line. There are big cups and small cups, all traveling to the packing department where they land in stacking tubes. A counter keeps a running tally on the paper cups and portions them out. The stacks of cups slide into a curtain of plastic. Hot jaws seal the plastic wrap around the stack. And now they're stacked, wrapped, and ready to be packed. Meanwhile, over in the testing department, the coffee is on, but this is no coffee break. They've pulled some cups off the production line to check for leaks. A mirror below reflects the situation. But leaks are 1 in a million, so they've made one leak deliberately to demonstrate for our camera. In the case of a real leak, they stop production and follow the paper trail, so to speak, until they determine the problem. It takes about a minute to transform pieces of paper into a cup. Now it's ready to hold some hot stuff without any leakage. The ancestor of the modern trumpet was a straight horn that could emit just a few notes. By the 15th century, they learned how to bend the horn, allowing for the use of crooks, or sections of bent tubing that changed the length of the instrument and the series of notes it produced. The invention of the valve in the mid-1800s finally allowed the trumpet to play in any key. A trumpet is made up of 1.5 meters of tubing. 3 valves allow air to flow through additional tubing to alter the trumpet's pitch. Trumpets are made from sheets of metal, most often brass. This factory combines different thicknesses in a single instrument to attain a particular sound. Workers first lay a template on a brass sheet and trace it out. Then they cut along the score line with electric shears. This piece will become the trumpet's bell. A manually operated press forms a perfect fold down the middle. Then they notch the edges. They close up the bell by hammering the notched pieces onto the opposite edge. They use a rawhide mallet because anything harder would damage the brass. They melt a brass alloy along the joint. It solidifies into a metal seam that bonds the edges to each other permanently. They slip the bell over a cone-shaped mandrel and hammer the brass until it too is cone-shaped. Then the bell goes onto another mandrel mounted on a lathe. They push the brass against the mandrel to finalize the shape. Then they file the metal smooth. Now for the bell's rim, called the bead. A brass rod with a notch at the end catches the edge of the bell and rolls it back into a rim. They use what's called a concave roller to round the rim's jagged edge. Then they slide a brass alloy wire into the rim pocket. This makes the bell stronger and adds weight to the edge of the flare to project sound better. They roll the rim over even more to enclose the wire. Now they heat the rim and apply acid flux to clean the surface for soldering. Lead or silver solder ensures the wire won't rattle when the bell vibrates. After wiping off the excess flux, they put the bell back on the lathe and scrape off the excess solder. Using an abrasive sponge, they smooth away any scratches left by the scraper. Then they remove any solder bits trapped in the rim. Now they fill the entire bell with a soap and water solution, then freeze it at -49 degrees Celsius. When the water has frozen, they place the bell in a bending block. The ice provides counterpressure, preventing the brass from buckling inward. The ice itself doesn't shatter under the pressure because the soap in the water makes it pliable. After checking the angle of the bend with a gauge, they let the bell defrost. In the mounting department, workers assemble smaller components made of brass and nickel, valve casings, the sliding tubes to which they connect, the slide for tuning the trumpet, the pipe that holds the mouthpiece. Then they solder on the bell. They lubricate 3 pistons and install one in each valve casing. These slides have to fit loosely enough to move freely, but tightly enough to prevent air leaks. One slide has a finger ring for holding the trumpet. After polishing and lacquering the brass, they test the trumpet for sound quality. This is one company that likes to blow its own horn.